Okay, as usual, I've drawn expertly this figure. And what you're dealing with here is a pole that is balanced on two counter-rotating wheels. And each of the wheels is rotating in the opposite sense. And so you kind of expect to get a vibration out of that. And what you're asked for is two fixed counter-rotating pulleys are driven at the same angular speed omega naught. Round bar is placed off center. Find omega n. The off-center distance is x on the figure. And so it might be easier on me to do this, which is to put a bar and start putting some forces down. So I have B here, I have NB, I have a rotation that's occurring, normal, mu k NA, and mg. So those are all sort of the standard things. Distance to the center of mass, distance to the other location is A, and the distance A over 2 x A over 2. So the center of mass is slightly offset with respect to the center of the two pulleys. So what's happening is that the rod, as it sort of vibrates, sort of shakes along and moves back and forth, or one direction, dependent on what's happening. But those are all of the forces that I have. I also know that this is occurring with a coefficient of kinetic friction because there's motion. It's not stopped, it's not sitting there, it's doing what it's supposed to do. So I have sum of forces in x, and that's going to be mu k NA minus mu k, and maybe before I do that, mu k NA and B is equal to mx double dot. So I know that whatever's happening to this thing, there's an acceleration in the x direction. I know that there is friction forces acting on both, and they're acting in the opposite sense because of the rotation. Sum of forces in y, NA plus NB minus mg is equal to 0. And again, despite the fact that reality would be that this thing would be bouncing and shaking, it's just shaking left to right. It's not moving up or down. And then finally, the sum of moments about A, and it would be NB, I'm going to do this a little differently, minus mg equals to 0. And just that A over 2 plus x. So that offset. It's 0 because this thing, despite the fact that a lot of things are happening around it, the rod itself is not rotating. So because it doesn't rotate, it just translates. It becomes a lot easier as a problem, and all I'm solving for are there. So I have three equations, three unknowns, NA and B and X, I guess. I can write everything and combine them together as I've done before, and I'll get UKG over A, x is equal to 0. And again, one of the things that comes out of all of these equations is, yeah, when we started this, we always talked about them in terms of k over m, square root k over m, and that's omega n squared. The term in front of x is always omega n squared, even if it isn't k over m. So this is the equivalent k equivalent over m equivalent square rooted, and that's what I'm going to be working with when I solve these problems. Omega n is equal to 2 mu kg over a, and for the frequency, it's 1 over 2 pi square root 2 mu k over a. It's one of those things that as you're going through all of these things, you don't want to deal with, you don't have to deal with very much. You know, like in this particular problem, the difficult part was this. And if you saw me at the beginning of lecture, I was furiously trying to white out everything that I had drawn because I had the wrong distances on the figure. But if you look at the figure there, I only have very few forces acting on this thing. I only have friction, I have normal forces, and I have the weight. And once you have all those terms in there, you can write an equation of motion. And I can do that in terms of any of the expressions here. Any questions? It's a rainy day. So as we sort of look at these problems, we always start with the same thing, which is these masses that are horizontally displacing. And I'm going to look at a couple different cases, and I got to remember if I did everything here. I have a system that is going to consist of a damper, a spring, and then this thing over here, which is another spring that's attached to the end of the mass but is displacing. And so it starts at a neutral position, which is the far left of those two blue rectangles, and it is displaced, and as it displaces, it stretches the spring. As the spring is stretched, there's a force applied, and that becomes a time-varying force. So in terms of what I'm looking at, same thing as before, I have a free body diagram, but I also have, say, a force that varies with time, sine omega t. So F naught sine omega t, which is kind of not going off to the side, it's horizontal. And that partially is described by the spring displacement. So I have a base excitation, and that's my B. I have a driving frequency, and I'm going to refer to that as omega. So it's another omega in there, but in this term, F naught sine omega t is equal to kb sine omega t. B. So I'm adding a displacement to the system. I'm moving things around and things are happening. And how that displacement can occur is any number of different ways. And I think this is from this text. I hope it is. But square waves, triangle, sawtooth. For example, in my research group, we're looking at burst modulation, and we're using square waves to drive MEMS-based devices as an aerodynamic control device. And one of the things we worry about are natural frequency and resonance frequencies, which start to play a role in this particular lecture. You can do funny things like half signs, general sort of signals, and those signals can vary with time, amplitude, period. You can add in a whole bunch of different signs and get all sorts of different things. But ultimately, its sum of forces x is equal to mx double dot, and so you can say minus kx minus x naught minus cx dot equals mx double dot. And that's the standard sort of form you're used to with everything there. Yep. Okay. But now I kind of have to look at minus k, and I think I'm going to switch my pen here. Minus k and x minus x naught minus cx dot plus some f naught sine omega t, which equals mx double dot. Now, of course, one of the things you should pick out right away is why didn't I make f naught sine omega t equal to a negative value? Because I can't. But the reason I didn't do that is because I just want to add in all the terms together, and I want to bring everything that's negative to the right-hand side and leave the f naught term on the left-hand side. So I'll end up with this expression, mx double dot plus cx dot plus kx is equal to f naught sine omega t. So the difference between these two cases, this is the unforced case, and this is the forcing. So I want to look in this particular lecture what happens when I add in an additional term to this. So again, one of the things that you worry about when you're doing any type of work of this nature is that you want to write something, not that. You want to write something that kind of makes some sort of sense. Kx equals kb sine omega t. So again, I can sort of point out in the work I do, and the work, actually the work that Professor Ho does, both of us are worried about resonance. And so we start to worry about what happens when you match up to the natural frequency of a system. And you worry about it because you want to force things simultaneously. So you end up with an equation like this. And once you do that, you of course rewrite it in this form. And now you have the same form as we had last time, but now we have a right-hand side to this. And that right-hand side is going to sort of affect things. So kb over m sine omega t, we've got to worry about that. But we also have a solution there that we know is equal to 0 in the unforced case. Let's make a first cut at this by assuming that the damping is 0. And so if the damping is 0, that second term goes away, so life becomes a lot easier, and it's x double dot plus omega n squared x, which equals, let me be even easier on myself. I have So I end up with this form of the equation, and I can write x now as a characteristic plus, or complementary, excuse me, it's different notation, different courses. Complementary solution and a particular solution. And the difference between these two set the right-hand side equal to 0, and the particular term keep forcing term. Ugh. So I have a solution that is going to sort of recognize that there is a natural frequency for this system, and that's the natural frequency we would be calculating anyways, and we've done before. But now I also have to look at a solution that's going to work for this particular case, and this is nice because it looks an awful lot like the solution I've had before, sines, and I know that the term on the left-hand side also kind of has sines. So if I look at the particular solution, I'm going to say x particular is equal to, let's make that a big X, sine omega t. And big X, once you solve it through, is going to take the form f naught divided by k, 1 minus omega natural squared. And so the x particular is equal to f naught divided by k all over 1 minus omega over omega n quantity squared sine of omega t. This is the steady state solution. As the complementary decays with time. So if in a typical case, I have a damper I've sort of applied to it, that is going to go away, and it will all depend on the particular solution that I've just solved for. And it will all depend on the forcing frequency applied, so that omega that you have in your solution. So I can look at an amplitude ratio. And just look at what's happening in terms of the deflection of this. And if I do that and I look at the ratio omega over omega n, I go from a magnification of 1 on the left-hand side as I approach the natural frequency of the system. I go towards a discontinuity, and then as I go away, I also have a departure from a discontinuous non-reasonable solution to one that does work. I used to refer to 1960s, 70s Chevy Novas because they were great if you drove them on the 401, at around 100, they would shake apart. But I don't think many of you know what a Chevy Nova was back in the 1970s, let alone the 1990s version. But what was interesting is the other day I was watching a video from a woman in the UK who was looking at the natural frequency of walking with your coffee cup. And she said that if you held it like this and you were walking, what happened is that you sort of amplified, you had a magnification factor that caused the coffee to slosh. And that the best way to walk with a cup of coffee was, one, you could walk backwards, in which case your frequency would go from 4 hertz to 1.7 hertz. Now, I'm not recommending that you go to Tim's and walk backwards. But the other one that was kind of interesting, I've tried it this morning, I don't know if it really works, is she suggested using a claw handle. And so as you're walking with your coffee cup, you walk like this, and what happens is you achieve the same frequency. So it's kind of cool, and I'm sure you can find it if you spend 2 minutes searching online. But the relevance to this is that life, first of all, makes sure that every one of your resonance frequencies are in your engineering regime, and your life becomes misery, and you have to figure out ways to damp it. And say, for example, the Taiwanese earthquake, the other thing that might be interesting is looking at how they do the damping of buildings. For example, the largest building in Taiwan, I think it's World Trade 1 or something, actually has a damper that was tested in Guelph, Ontario. And it was part of their wind engineering work with RWDI. So there you go. So magnification, as you approach the natural frequency of a system with your forcing, you start to amplify disturbances. And those amplifications make things very miserable. So M approaches infinity as omega approaches omega n. So if omega is less than omega n, then M is positive and the vibration is in phase with the force. If omega is greater, M is negative, and vibration is out of phase with the forcing. What happens if zeta, or well, what happens if C is not equal to 0? And I understand if you are looking carefully at the syllabus, we don't really talk about this, but it's worthwhile taking a small divergence in that direction. So if C is not equal to 0, what ends up happening is you end up with this equation, which was the one I sort of started with. That is, you have all of the standard terms on the left-hand side, all of the forcing terms on the right-hand side. And again, as much as possible as you're looking at this, remember, I'm keeping everything positive in my solutions. So the particular solution is going to be x sine omega t plus x, well, x1, x2 cos omega t. X particular is also x sine omega t minus phi. I'm not going to have a lot of room on this one. That kind of changes your solution form, and it ends up looking 1 minus omega over omega n squared, which was the same as before, squared, plus 2 zeta omega over omega n squared to the 1/2. And phi is your phase separation, and it's inverse tan of 2 zeta omega over omega n, 1 minus omega over omega n quantity squared. In your solution, not to forget that, c e to the minus zeta omega nt sine omega dt plus psi plus x, let me call that xa so I don't mess that up, sine omega t minus phi. And that's assuming an underdamped case. And so you have a solution that combines both the zero case, which is the left-hand side, which didn't really come across very well, plus the particular solution, so the complementary plus the particular. So this sort of looks, and these depend on initial conditions as usual. So the impact of that is that if you're driving on the road without any shock absorbers, your car shakes apart uncontrollably. And dependent on the engineer designing things and what they want you to feel as you drive, they can adjust the amplitude of the vibration so that you don't have your teeth shattered at the end of your drive to Montreal. Okay, squiggly, zeta, okay. And so you can see that the effect can be quite significant in terms of what it drops and how far it drops. So how does that change the magnification factor? The magnification factor becomes 1 over 1 minus omega over omega n squared plus 2 zeta omega over omega n squared to the 1/2. So you're adding in a term that gets rid of a zero case in your solution, or helps to deal with. Don't want to say anything more about that. I mentioned earlier, so for omega less than omega n, you have a slight shift and it leads. When its omega is greater than omega n, it's out of phase and it's slightly, well, it's lower, but it's also, it lags the natural frequency of the system. Questions? All of that's just to say, ultimately, you have one solution to every problem in this chapter, but you can simplify things depending on what you're dealing with. But each of the cases, if you look at, in our case, you look at the zero case for x double dot plus of c over m x dot plus k over m x equals 0. That's the general solution. When you have forcing, we in this course do not have any terms left. Okay. Let's try one out. We have a block, and A, B, no, maybe not like that. So one of the things that you often worry about when you're doing work over in a lab is measuring things properly. And so you spend a lot of time sort of attaching scales to things and making sure that things are not moving and confirming that you're measuring what you think you are. So block and platform are coupled to base B with a linear spring. The combined mass of the block and platform is 1.5 kilos, and K is equal to 50 newtons per meter. Vibration is sinusoidal with an amplitude of 5 millimeters. Find the vertical motion of the platform and block as a function of T. So I have this system here. I have MAG, I have force of the spring, and again you'll notice that when I'm writing this out, I'm always writing it out in this form right here, which is everything is going to work out, so I have a positive equation. When I put things down on scales, of course, they displace. And if I do this as a static equilibrium problem, they displace a certain amount. So I can consider that y sub a. So that's where I start. So that's my static equilibrium position. And I'm going to consider that. And this is a nice problem because there's no rotation. Oh. So if I look at sum of forces in y, I only have two. I have minus force of the spring, minus the weight of the platform and the box, and I have acceleration y. Force in the spring is going to be k ya minus yb minus delta s. Acceleration in y is equal to y to y double a, and I'm going to define y sub b, which is yb sine of omega bt. So the platform, you're told, is varying sinusoidally. It has a 5 millimeter oscillation, and so I have to consider that in my term y sub b because it's not sort of sticking around and doing nice things. So when I write that out, I can say minus k ya minus yb sine omega bt minus delta s minus mg equals ma ya, double dot. So get rid of the static equilibrium term as usual because you don't want to deal with it. You don't need to. Then you have mass and terms. So you can write y double dot a plus k over m a y a equals k y b m a sine of omega b t. So I've written at that point a full form of the equation. I don't have any damping in this, so it will not go toward, it will not decrease in amplitude, but on the right-hand side, this will make up my complementary solution, this will make up my particular solution. And in this case, too, I know YB is 5 millimeters, so that I could save myself a little bit of trouble, but that's okay. So YA is equal to C sine omega nt, which is the complementary solution over there where I set it equal to 0, plus d cos omega nt, plus yb 1 minus omega over omega n squared sine, did I refer to, okay, I did refer to this as omega b. Omega b squared over sine omega bt. So I have a complementary solution. I know that everything starts at the 0 location, so everything starts from rest. Ya of 0 equals 0, Ya dot of 0 equals 0, and immediately I don't need to worry about the cosine term. And I will end up with a mess of terms, but if minus omega b over omega n squared. So I have the constant, I have all the terms I need. I also know that the natural frequency of the system, omega n, is going to equal square root k over m a, which is equal to 5.77 rads per second. Omega b equals 15 hertz, or 90, well, that's actually F rads per second. So Ya equals 0. Actually, I don't need to do that. I didn't write it down. Ya equals a Fourier sine wave, and so it looks Ya equals 0.31 sine of 5.77 t minus 0.019 cos of 94.25 t in millimeters. Again, as much as possible, you are not doing a lot of analysis on this. You are just solving these problems. I'm going to get it right. There we go. You are just solving these problems based on the free body diagram, writing out the terms, and then once you've written out the terms, you can solve for the particular definitions. Those definitions just depend on how you define everything in these particular cases. So you end up with a solution here, which is very low frequency, high amplitude, 0.31 sine 577, and a very low amplitude, high frequency component, which is the Furry bit that you see on the sine wave. So it just sort of doesn't change the actual overall amplitude that much, but it introduces a secondary vibration. Okay. All right, so we have a final example. I'm not sure how far I'll get on this. Yeah, who knows? This is a point mass. And it has a mass of 1.4 kilos. The rod is 1 meter and 1.8 kilograms. And here, there's a torsional spring. And you've seen these things if you've ever taken apart an old-fashioned clock. They're the springs that you use to wind them up. So you have a K, which is there. So this is, say, for an amusement park ride. You want the door to open as the person passes and then immediately close, and then the next person can pass. And you're asked to find K of this torsional spring and the critical damping coefficient for a return to 3.5 degrees at a time of 2.5 seconds, starting from a theta naught of 85 degrees. Anything missing on this? So theta, just for completeness, is there. So you're given all of that. And of course, where you start in all of this is the same place. You have reaction force at the pin. You have the moment of the spring and moments, you can call it D, mass of B, mass out here. So point O is right here. So if I'm looking at this, I'm going to do sum of moments about O. And it'll be sum of moments about O. And I don't have to worry about the mass in that direction unless it's vertical. So I don't think it's vertical in this case. So, sorry, there should also be, and the critical, oh yeah, there's a damping coefficient. So there's the damper. So MS is K of the torsional spring theta. Mass of the damper is C of the torsional, essentially it's the same thing, but C of the torsional spring and theta dot. So if that's the case, I can put all the terms in there, so those are causing moments. And alpha is equal to theta double dot, so that I can do the same thing as I've done before. All right. I naught, what is I naught going to be? So I have a rod that's pinned at one end, and it has a mass. So I naught in this case is 1/3 m of the rod or bar L squared plus m L squared. Actually, I'm just not going to. Where m is the mass of the point mass. I really should use better bar. And I'm going to just sort of say that that is 1/3 m mass of the bar plus mass times L squared theta double dot plus CT theta dot plus KT theta is equal to 0. And so bar so there you go. Once you've done that, you've solved the problem. Because again, you're not doing anything special to these problems. You're just going to divide everything in front of theta double dot and bring it over here. You've set it up the correct way with plus and plus, and everything should work at that point. So omega n of this system is KT 1/3 mb plus mass times L squared, which equals 0.71 square root of KT. Theta is equal to A plus BT e to the minus omega nt, because this is a critically damped problem, and theta is equal, theta dot is e to the minus omega nt plus A plus BT minus omega n e to the minus omega nt. You're given theta at 0 equals 85 degrees, which equals 1.4835 rads. Theta dot at 0, or no, 2.5 seconds, is equal to 1.049 omega n. And so if you put in the terms, you end up with theta at 2.5 seconds equals, oops, no, you're given theta at 2.5 is equal to 3.5 degrees. Put everything together, you end up with a KT, which is equal to 8.27 newtons per rad, and a CT, which is 8.13 Newton seconds per rad. Okay, where am I at? Okay. And I can put the solution. Let's see if I have the solution. And all of this is coming from this. Take the derivatives, calculate all the terms, you have everything you need. You can solve for theta at 0, you know what that has to equal. Theta at 0 is going to be b plus a times b minus omega n, which gives you 85 degrees or 1.4835 rads. Theta at 2.5 is going to be another value. You also have theta at 0, or theta dot at 2.5 seconds is 1.4049 omega n. There. Any questions? This is a lot. It's all obvious. I don't need to do anything. So Monday I will sort of go off a little bit off course topic, and I'm going to look at work energy because I think it's still worthwhile doing because I actually like it, and it's something I think I should talk about a little bit. We will finish off vibrations entirely on Wednesday next week, and then Thursday it will be the end of the course.